Hello students, myself Brinda Patel, Assistant Professor in Computer Engineering Department at Sri Swaminarayan Institute of Technology. So today we are going to start unit chapter number 7 of unit 5, which is wavelets and multi-resolution processing. So we will continue with background, introduction, multi-resolution expansion and wavelet transforms. So let's start with introduction. So the Fourier transform has been the mainstay of transform based image processing since the late 1950s. So a more recent transformation known as a wavelet transformation. So it is known as a wavelet transformation. So it is making it even easier to compress the image, transmit the image and analyze to many images. So the Fourier transform whose basis functions are sinusoids. So wavelet transforms are based on the small waves. It is known as the wavelets or varying frequency and limited duration. So this allows them to provide a equivalent of a musical score of an image, relieving not only what notes to play but also when to play them. So Fourier transform on the other hand is provide only the notes or frequency information, means temporal information. So the temporal information is lost in the transformation process. So the wavelets are the first shown to be the foundation of a powerful new approach to signal processing and analysis known as a multi-resolution theory. So multi-resolution theory incorporates and unifies techniques, right? Which techniques? So subdecoding from a signal processing, quadrilateral mirror filtering from digital speech recognition, and pyramidal image processing. So multi-resolution theory is what it concerned with the representation and analysis of signals at more than one resolution. So the appeal of such approach is obvious. Features that might go detected at a one resolution may be easy to detect another. So generally we see the regions of similar textures, intensity levels that combines from the objects. So if the objects are small in size or low in contrast, so we normally examine them at a high resolution. So if they are large in size in contrast, so coarse view is all that is required. So if both small and large objects or low and high contrast objects are present simultaneously, it can be advantageous to study them at several resolutions. So from the mathematical viewpoint, images are two-dimensional arrays of intensity values with locally varying statistics that results from different combinations of arced features like edges and contrasting homogeneous regions. So as here this image that examined repeatedly in a remainder of sections. Right? So local histograms can vary significantly from one part of image to another. So making statistical modeling over the span of the entire image a difficult or impossible task. So let's see about image pyramids. So it is a powerful, conceptually simple structure of representing the images at more than one resolution. So it is known as the image pyramid. So it is originally devised for machine vision and image compression applications. So an image pyramid is a collection of decreasing resolution images arranged in the shape of a pyramid. So here we can show in this figure the base of the pyramid contains the high resolution representation of the image being processed. So the approx contains a low resolution, which is the approximation. So as you move up to the pyramid, both size and resolution decrease. The base level Z is the size of 0, right? So the base level has a size of 2 raised to j into 2 raised to j or n by n, where j is equal to log 2 n. So apex level is 0 of size 1 cross 1. Here is the apex level of 1 cross 1, and general level j is of size 2 raised to j into 2 raised to j. So the pyramid we can see here is composed of the j plus 1 resolution levels from 2 raised to j into 2 raised to j to 2 raised to 0 by 2 raised to 0. So most image pyramids are created to p plus 1 levels. So the total number of pixels of level p plus 1 pyramid is for p greater than 0 is n square into 1 plus 1 by 4 raised to 1, 1 by 4 raised to 2, 1 by 4 raised to p is less than is equal to 4 by 3 n square. So here this figure shows the simple system constructing two intimately related images pyramids. So the level j minus 1 approximation output provides the images needed to build an approximation pyramid. All the level j prediction residual output is used to build the complementary prediction residual pyramid. So approximation pyramids, prediction residual pyramids contain only one reduced resolution pyramid, right? So here at the top of the pyramid, here the level is j minus p. So all other levels contain prediction residuals, where the level j prediction residual is defined as a difference between the level j approximation. At an estimation of level j approximation is based on the level j minus 1 approximation. So this figure shows both approximation pyramid and a prediction residual pyramid. So a low pass Gaussian smoothing filter was used to produce the 4-level approximation pyramid. So as you can see here, the resulting pyramid contains the original 512 by 512 resolution image and 3 low resolution approximations. So here a bilinear interpolation filter was used to produce the prediction residual pyramid. We can see it in figure B. So in the absence of the quantization error, the resulting prediction is residual pyramid can be used to generate a complementary approximation pyramid. So including the original image without error, we begin with the level 6, which is 64 by 64 approximation image. Figure B is highly picked around 0. The approximation histogram is not. So unlike approximation images, our prediction residual images can be highly compressed by assigning fewer bits to the more probable values. So this figure scales to make the small prediction error more visible. Now subband coding, right? So another important imaging technique that ties to multi-resolution analysis is subband coding. So in subband coding, an image is decomposed into a set of band limited components known as the subbands. So the decomposition is performed so that the subbands can be reassembled to reconstruct the original image without error. Because the decomposition and reconstruction are performed by means of the digital filters, we begin our discussion here with the introduction of a digital signal processing DSP and digital signal filtering DSF. So here the digital signal filtering consider two-band subband coding and decoding system as here. So as indicated here in this figure, the system is composed of two filter banks, right? So each containing two FIR filters of the type here. So each of the four FIR filters is depicted as a single block, as here they are here are the two blocks. So in this figure, with the impulse response of each filter written inside it, the analysis filter bank, which includes filters H0 and H1n, are half band filters, so whose idealized transfer characteristics H0 and H1 here are. So filters H0n is a low pass filter whose output is subband FLP of n is known as approximation of Fn, and filter H1n is high pass filter whose output is subband FHP of n is known as a high frequency or detail part of Fn, right? So the input and output of the subband and decoding system are identical. When this is accomplished, the resulting system is said to employ perfect reconstruction filter. So now let's see about the Haar transform. So the third and final imaging related operation which ties to multi-resolution analysis that we look at is the Haar transformation, Haar transform. So within the context of here, it is important system, it is important stream for the fact that its basis, the context of the function, are the oldest and simplest known as the orthonormal wavelets. So Haar transform can be expressed here, T is equal to H F H. So here F is an n by n image matrix, H is a n by n Haar transformation matrix, and T is a resulting n by n transform. So the transpose is required because H is not symmetric. So here by this equation, the transformation matrix is assumed to be symmetric. So for the Haar transform, H contains the Haar basic functions Hk of Z. So here to generate H, we define the integer k, such as k is equal to 2 raised to p plus q minus 1. So where 0 less than p less than equal to p less than equal to n minus 1, q is equal to 0 or 1, and for p, here p is equal to 0 and 1 less than equal to q less than equal to 2 raised to p, for p is not equal to 0. So the Haar basis transformation function is h0 of z is equal to h00 of z is equal to 1 upon root n, where z belongs to 0 to 1. So hk of z will be with the value of k, we can see here 1 upon root n, when q minus 1 by 2 raised to p, then it will 2 raised to p minus 2. When q minus 0.5 by 2 raised to p less than equal to z and less than q by 2 raised to p, it will be minus 2 raised to p by 2, and otherwise it will 0. Limit is 0 belongs to 0 to 1. So the ith row of an n by n Haar transformation matrix contains the elements of hi of z, right? For z is equal to 0 by n, 1 by n, 2 by n up to n minus 1 by n for the instance of n equal to 2. So here is one example. It shows the decomposition of the 512 by 512. So that combines the key features of pyramid coding, subband coding, and the Haar transform. So figure A here is a represents the local histograms, right? So many of the pixels are close to 0 because the sub images, and the large number of zeros in the decomposition makes the image an excellent candidate for compression. Then we will see figure B. So in a manner that is similar to way in which the levels of the prediction residual pyramid of here. So in this figure we used to create approximation images of differing resolutions. Figure B through D, we are of a size 64 by 64, 128 by 128 and 256 by 256 respectively. So we are generated from the sub images, right, from here. So now multi-resolution expansions. So here multi-resolution analysis means MRA. So it is a scaling function which is used to create a series of approximations of a function or image. So each difference in information between the adjacent approximations, right? So the additional function known as the wavelets which are used to encode the difference in information between adjacent approximations. So now let's start with series expansions. So signal or a function of fx can be better analyzed as a linear combination of expansion functions. So f of x is equal to sigma k alpha k psi k of x, where k is an integer index of a finite or infinite sum. Alpha k are the real valued expansion coefficients and the psi k of x are real valued expansion functions. So here there are two cases. So these cases are using vectors in two-dimensional Euclidean space. So case 1, if the expression function from the orthonormal basis for V, which meaning that psi j of x, psi k of x is equal to del jk is equal to, when j is not is equal to k then it will 0 and j is equal to k then it will 1. Second case is the expansion functions are not orthonormal but are an orthogonal basis for V. Then it will be psi j of x, psi k of x is equal to 0, where j is not is equal to k. And the basis functions and their duals are known as the orthogonal. In case 3, if the expansion set is not a basis for V but supports the expansion defined, so we will see it is spanning set in which there is more than one set of alpha k for any f of x belongs to V. So they form a frame in which a f of or f of x square less than is equal to sigma k psi k of x f x raised to square less than is equal to b f of x square. Now the scaling functions. So consider the set of the expansion functions composed of integer translations and binary scaling of a real square integrable function psi of x. So this is the set psi of x uh, and k of x, where psi j k of x is equal to 2 raised to j by 2 psi 2 raised to j x minus k. So here k determines the position of psi j k of x along with the x axis and j determines the width of the psi j k of x. So here how broad or narrow it is along the x axis. So the term 2 raised to j by 2 controls the amplitude of the function because the shape of psi j of k of x changes with the j. So psi x is known as a scaling function, right? So by choosing psi of x properly, it can be made to span L square of R, which is a set of all measurable square integrable function. So in this figure A to D, it shows the 4 of the many expansion functions that can be generated by substituting this pulse shaped scaling function. So here note that the expansion function for I j is equal to 1 in figure C and in figure D are half as wide as those for j is equal to 0 in figure A and figure B. So for a given interval on x, we can define twice as many v1 scaling, right? So this figure shows the member of subspace v1. So this function does not to belong to v0. And here figure A and figure B are two codes to represent it. So high resolution functions like figure C and figure D are required. So they can be used in here. Now MRA requirements. So the simple scaling function in the preceding example obeys the four fundamental requirements of multi-resolution analysis. So first MRA requirement 1 is the scaling function is orthogonal to its integer translates. So this is easy to see that in case of the higher functions, because whenever it has a value of 1, its integer translates are 0, so that the product of the two is 0. MRA requirement 2. So the subspaces spanned by the scaling function at low scales are nested within those spanned at higher scales. So subspaces containing high resolution functions must also contain all lower resolution function. Requirement 3. So the only function that is common to all Vj is f of x is equal to 0. So it is considered the coarest possible expansion function. For example, j is equal to minus infinite. So the only representable function is the function of no information. So that is v minus infinite is equal to 0. Now requirement 4. So any function can be represented with the arbitrary precision. So through it may not be possible to expand a particular f of x at any arbitrarily coarse resolution, as was the case for the function. So all measurable square integrable functions can be represented by scaling function in the limit as j is equal to infinite. So here wavelet functions. So given a scaling function that meets the MRA requirements of previous section, so we can define a wavelet function psi of x that together with the integer translates and binary scalings spans the difference between any two adjacent scaling subspaces Vj and Bj plus 1. So the situation is illustrated graphically here. We can see. So psi j of k of x is equal to 2 raised to j by 2 psi 2 raised to j x minus k. So for all appropriate j, k and l belongs to z, v2 is equal to v1 or v1, w1 is equal to v0 or w0 or w1. So now here a wavelet function of wx together with its integer translates and binary scaling spans. So the difference between any two adjacent scaling subspaces Vj and Vj plus 1, so which is psi jk of x is equal to 2 raised to j by 2 psi 2 raised to j x minus k. So for all the k belongs to z that span wj spaces in here. So as with scaling functions, we can write psi x is equal to sigma h psi of n root 2 psi 2x minus n, and similarly here h psi of n is equal to minus 1 raised to n h psi 1 minus n. So here this figure shows the function of subspace v1 that is not in subspace v0. So this function was considered in an here through the example. So although the function cannot be represented accurately in V0, it indicates that it can be expected using V0 and W0 expansion functions. So the resulting expansion will be f of x is equal to fa of x and fd of x. Now wavelet transformation in one dimension. So we will see about the wavelet series expansions. So wavelet series expansion of function f of x belong to L square of r is relative to wavelet psi of x and scaling function psi of x. So in accordance here, some number of wavelet function expressions in subspaces wj0, wj plus 1. So we can define it as a f of x is equal to sigma k cj0 of k psi j0 of k of x plus sigma j is equal to j0 to infinite and k dj of x k psi j k of x. So j0 is an arbitrary scaling scale, and here cj0k and dj of k are reliable to alpha k respectively. So here if the expansion functions from the orthonormal basis or tight frame, which is often the case, the expansion coefficients are calculated based on these equations, right? So now this figure, it is using a Haar wavelets. So and a starting scale is j0 is equal to 0 can be used to compute the equations. So here this approximation is shown in this figure and its average value of the original function. The second term uses d0 of 0. So here this additional detail is shown in this figure, B, C and D and E, and the resulting V2 approximation is depicted to F. Now the discrete wavelet transform. So like the Fourier series expansion, the wavelet series expansion of this maps a function of continuous variable into sequences of coefficient clients. So if the function is being expanded, it is discrete. So here the resulting coefficients are known as the discrete wavelet transform DWT. For example, if f of n is equal to f of x0 plus n del x, so for x0 del x and n is equal to 0, 1, 2 up to m minus 1, the wavelet series expansion coefficients of f of x become forward DWT coefficients for sequences f of n. So w psi j0k and w psi jk. So we will get here these equations. So here w psi j0k and w psi jk in these equations are sampled version of the basic functions psi j0k of x and psi jk of x, right? So the complementary inverse of dWt is here. Now the continuous wavelet transform. So the natural extension of the discrete wavelet transform is a continuous wavelet transform CWT, which transforms a continuous function into a highly redundant function of two continuous variables, translation and scale. So the continuous wavelet transform of a continuous square integrable function f of x relative to the real valued wavelet psi of x is defined as w psi s of t and here. So Here S and T are known as a scale and translation parameters. So given this, it can be obtained using the inverse continuous wavelet transform, right? So the equation will be this. So here C psi is equal to minus infinite to infinite, the limit is, and psi u raised to square upon mod u du, and here this psi u is the Fourier transform of psi x, right? Thank you.